Hello students, up to now we have discussed the three units of electronic circuit analysis. Now we are in the unit number 4, which is called power amplifiers. In this unit we are going to discuss about different types of the power amplifiers like class A, class B, class C, class AB, class D and class S type of power amplifiers. And also we are going to discuss about their efficiencies and also MOSFET power amplifiers, thermal stability and heat sinks. So let us see what is meant by this power amplifier first. So the power amplifier is also called as large signal amplifier. Firstly, we will see about the definition for the power amplifier. The power amplifier is also called as large signal amplifier. Is an electronic device which provides sufficient power to an output load to drive speaker or other power device. It delivers a few watts to tens of watts. There is one more definition for the power amplifier, which is an amplifier delivering more than 1 watt power to the load is called power amplifier. The main purpose of this amplifier is to raise the power level of the input signal to get the large power at the output. So the main thing is these power amplifiers will increase the power level of the signal. We all know the power is a product of voltage and current. So the power amplifiers will increases the strength of a signal in terms of a voltage and current too. So here we can see the basic idea of an amplifier, which containing many stages here. These all are voltage amplifier stages and the last stage is a power amplifier stage. So this amplifier section will take the input from the microphone and drives a loudspeaker. So the input from the microphone is in order of microvolts, and these microvolts voltage will be amplified by the voltage amplifier sections and which delivers some few volts. So this voltage will be given as the input for the power amplifier. So where the voltage and current both amplification is done, which means in which the most of the power amplification is going to be done, and later on this power will be delivered to the loudspeaker. So this type of power amplifiers are used in public addressing systems, radio receivers and tape recorders and TV receivers, etc. So let us see the features of the power amplifiers. So as we already discussed, the input power for the power amplifiers is large in order of few volts because the before stages of this power amplifier are all are voltage amplifiers, so that the output voltage is in order of volts. So the second thing, the output has large voltage and current swings. Why means it is increasing the power level of the signal, the voltage and current both has large swings. The H parameter analysis is not applicable for the power amplifiers. Nextly, the power amplifiers are used where the impedance matching is required because the maximum power can be transferred from the amplifier to the load when the both impedances are matched, which means that the output impedance of an amplifier must be matched with the input impedance of the load. So as we are using CC amplifiers as a power amplifiers which is having low output impedance that can be matched with the input impedance of the loads, and these power transistors are different from the normal transistors because they are dealing with more power. They may develop more heat, so that the power transistors definitely used with the heat sinks in order to dissipate the heat developed in it. So as we are handling with the large powers, the size of an amplifier becomes bulky because the transistor size itself becomes large. So in these power amplifiers, harmonic distortion is present. So these power amplifiers are mainly used in audio circuits. Hence, it is also called audio frequency power amplifiers. The impedance matching. Why the impedance matching is required? We already discussed it. In order to deliver more power to the load, the output impedance of an amplifier must be matched with the input impedance of the load. Then only the power developed in the amplifier will be transferred to the load. Based on the operating point and input voltages, these power amplifiers are classified as Class A, Class B, Class C, Class AB, and Class D. So later on we will discuss about these topics. In the last video, we have seen about the classification of power amplifiers based on their operating point and input voltage. They are classified as Class A, Class B, Class AB, and Class C. The Class A power amplifier is an amplifier in which collector current will flow in all times during the full cycle of input signal, which means that the 360 degrees of input signal will be reproduced at the output side. We can understand from this diagram the entire input signal will be reproducing at the output side of the Class A amplifier. So let us see the Class B amplifier. So in Class B amplifiers, only one half cycle will be reproduced at the output side. If you see this graph, this is the input signal. So only one half cycle is reproducing at the output side. Only 0 to pi is reproducing at the output side, and the remaining half cycle will be discarded. This type of an amplifier is called Class B type of power amplifier. So let us see the Class AB type of power amplifier. So in this type of amplifier, so output current will flow more than 180 degrees and less than 360 degrees, which means that from this graph, this is the input signal and this one is the output signal. In the output signal, we can observe that it is providing more than 180 degrees and less than the 360 degrees of input cycle. Okay, let us move to the Class C type of power amplifier. In Class C type of power amplifier, the output collector current will flow less than one half cycle, which means that less than half cycle is producing at the output. So here we can see the input half cycle is this, and if you see the output half cycle, it is producing less than 180 degrees. Okay, these are all the classification of power amplifiers. And let us move to the Class A large signal or Class A power amplifiers. So the Class A large signal amplifiers are classified into series fed or direct coupled Class A power amplifier, and the second classification is transformer coupled Class A power amplifier. So let us move to the series fed Class A power amplifier first, and this is the circuit diagram for series fed Class A power amplifier. So this is just fixed bias CE amplifier, but the transistor used here is not a normal transistor, it is a power transistor. Okay, here RL is the load resistance and RB gives the biasing. RB provides the biasing. So VIN is the input AC signal and VCC is the DC supply voltage for the circuit, and VBE is the voltage between base to emitter, and VCE is the output voltage. Okay, in this one, RL is the load resistance that is directly connected between the VCC and collector of the transistor. The efficiency of series fed Class A power amplifier is only 25%. That is a very less. Let us see the advantages and disadvantages of series fed Class A power amplifier. The advantages are circuit is simple because we are using less number of components, and that it is cheaper because load is directly connected to the collector. We are not using any impedance matching element like transformer here, that's why it is cheaper. And the third one is less number of components that are used. Let us go to the disadvantages of series fed class A power amplifier. If you see, because the load is directly connected to the collector circuit, more power is getting wasted. Power will be wasted in the form of heat. So definitely we have to use the heat sinks. That is the one more disadvantage. If you see one more disadvantage in series fed class A amplifier, that is impedance matching. The output impedance is high, so that we cannot directly connect a loudspeaker to our series fed class A amplifier, because the loudspeaker has the input impedance around 4 ohms to 16 ohms maximum. So the maximum power cannot be delivered to the loudspeaker. That is the one more disadvantage. And last disadvantage is efficiency is poor. It is just a 25%. So because of these disadvantages, we are moving to the next type of class A power amplifier, that is transformer coupled class A power amplifier. This is the circuit diagram for transformer coupled class A power amplifier. So the only difference here is RL is replaced with the transformer primary winding. So here we are using one impedance matching transformer. So this transformer primary is connected as a load resistor to our class A power amplifier, and we are adding the load to the secondary of the transformer. Here RB provides the biasing, and VCC provides a DC supply voltage, and VIN is the AC input signal. Before going into the operation of the circuit, we should know some concepts regarding the transformer. They are: this is a transformer in which V1 is the primary voltage and V2 is the secondary voltage. Here I1 is the primary current, I2 is the secondary current. Here RL is the load resistance and RL dash is the effective load resistance due to RL in the secondary. So the basic concepts we should know about the transformer are: first one, transformer turns ratio. It is the ratio of number of turns in the secondary to the number of turns in the primary. So N is the notation for the transformer turns ratio, that is equal to N2 by N1, where N2 is the number of turns in the secondary and N1 is the number of turns in the primary. Voltage transformation. Transformer transforms voltage applied at one side to another side, which is proportional to the transformer turns ratio. So V2 by V1 is equal to N2 by N1. So here V2 is the secondary voltage and V1 is the primary voltage, which is proportional to transformer turns ratio N2 by N1. Next one is the current transformation. The current produced in the secondary is inversely proportional to the turns ratio. I2 by I1 is equal to N1 by N2, which is the reciprocal of the turns ratio 1 by N, that is equal to V1 by V2 from the voltage transformation equation. Next, impedance transformation. As like how the voltage and currents are transforming from one winding to another winding, the impedance also transforms from one winding to another winding. And we know that, see, V2 by V1 is equal to N2 by N1, which is voltage transformation equation, and I2 by I1 is equal to N1 by N2, which is the current transformation equation. So RL is a load resistance that is connected at the secondary of our transformer, and RL dash is called effective load due to the RL in the secondary, or it is also called reflected load resistance or transformed load resistance. From the Ohm's law, we know that R is equal to V by I. So we can say RL is equal to V2 divided by I2, and RL dash is equal to V1 divided by I1. Similarly, the same equations are given here. RL is equal to V2 by I2 and RL dash is equal to V1 by I1. So from these voltage transformation equations and current transformation equations, we can rewrite the equations for V1 and I1. The V1 can be written as V2 into N1 by N2 and I1 can be written as I2 into N2 by N1. Substituting the values of V1 and I1 in RL dash equation, we will get RL is equal to V2 into N1 by N2 divided by I2 into N2 by N1. So which results N1 by N2 whole square into V2 by I2. So what is V2 by I2? So V2 by I2 is nothing but RL. So we can write the effective load resistance RL dash is equal to N1 by N2 whole square into RL. So in general, the effective load resistance in the primary side is greater than the load resistance RL. Next thing, we have to find the efficiency. The overall efficiency of an amplifier circuit is given by eta is equal to AC power delivered to the load to total power delivered by DC supply, PAC divided by PDC. This efficiency has the notation eta and it is always expressed in percentage. So eta percentage is equal to PAC divided by PDC into 100. So in order to get the efficiency of our amplifier circuit, we should know the values of AC power and DC power. So DC power can be written as, we know that the power is a multiplication of voltage into current. So we are finding that DC power PDC, which is a multiplication of DC voltage VCC to the DC current ICQ, where ICQ is the Q point collector current. In this graph, we can see the AC load line and DC load line, which are drawn on output characteristics of our amplifier. So here the slope of the curve is -1 by RL dash. So the Q point is located exactly at the middle of the DC load line. So this is the input signal and this one is the output signal. So this is the V maximum point and V minimum point. In order to get one peak value, we have to do V max minus V minimum by 2. Here also I max minus I minimum by 2 will give you one peak value. AC operation. So when we apply an AC input signal to our amplifier, then the output current and output voltage will vary sinusoidally, which produces an AC signal at the output side, and that produced AC signal will be delivered to the load. We have to find the AC output power. The AC power developed on the primary is given by P is equal to V1 RMS into I1 RMS. So V1 is the primary voltage and I1 is the primary current. So these AC voltage and AC currents are always represented in the form of RMS values, root mean square values. So this V can be written in terms of I as V is equal to IRL, so that the equation can also be written as I1 square RMS into RL dash, or else if we replace I in terms of V, I is equal to V by R. That's why we will get V1 RMS square divided by RL dash. So the RMS values can be written as V1 by maximum value divided by root 2 and I1 RMS can be written as I1 maximum divided by root 2. That is equal to V1 Im by 2. If this root 2 will get multiplied, we will get 2. So in terms of I, this PAC can be written as I1 square RMS RL dash by 2, or else in terms of voltage it can be written as V1 square RMS by 2 RL. So the AC power delivered to the load on the secondary is given by PAC is equal to V2 RMS into I2 RMS. Here V2 is the secondary voltage and I2 is the secondary current. RMS is the AC representation of voltage and currents. This can be written as I2 square RMS RL dash or V2 square RMS by RL dash. Okay, so if the V2 RMS can be written as V2 maximum by root 2 and I2 RMS can be written as I2 maximum by root 2. These root 2's will get multiplied and becomes 2. So V2 maximum into I2 maximum by 2. This can also be written as in terms of I only I2 square RMS RL dash by 2 V2 square RMS divided by 2 RL. As we have already discussed, the slope of AC load line is 1 by RL. 1 by RL, which can also be expressed in terms of the primary current and primary voltage as I1 maximum by V1 maximum. The expression for the AC power delivered to the load is given by, already we have seen the PAC is equal to V2 maximum into I2 maximum by 2. The V2 maximum can be written as V max minus V minimum by 2 and I2 maximum can be written as I maximum minus I minimum by 2, so that the equation will becomes V max minus V minimum into I max minus I minimum by 8. For maximum efficiency in the transformer coupled amplifier, V minimum is equal to 0 and V maximum is equal to 2 VCC, and similarly the I minimum is equal to 0 and I maximum is equal to 2 ICQ. The efficiency eta is equal to PAC by PDC into 100. Here PAC is equal to V max minus V minimum into I max minus I minimum by 8, and the DC power is equal to VCC into ICQ, which is already derived. So if we substitute these values from the figure, the equation can be simplified to 1 by 2 into 100, that is equal to 50%. Therefore, the efficiency of transformer coupled class A amplifier is equal to 50%, which is double for the series fed class A power amplifier. So that by using the transformer coupled class A power amplifier, we can increase the efficiency to 50%. But in practical, the efficiency is about 30% to 35%. So maximum power dissipation. So the maximum power dissipation in the sense how much power was wasted in the form of heat. So here the PD is the dissipated power, which is DC power minus AC power. Here AC power is the useful power and DC is the supplied power. So here PD is the wasted power. The maximum power dissipation takes place when the AC input signal is 0. Therefore, the maximum power dissipated PD maximum is equal to VCC into ICQ, which is nothing but the DC power. Let us see the advantages of transformer coupled class A amplifier, which the efficiency is higher than the direct coupling or series fed class A amplifier. So in series fed it is 25%, in transformer coupled it is 50%. Because of using transformer, the DC is getting blocked. So we are using transformer, so the DC will get blocked. It provides impedance matching, so which is not in the series fed class A amplifier, as we are using transformer that provides impedance matching. Disadvantages. If you see the disadvantages, we are using transformer. The transformers are bulky devices and they are costly. That is the main disadvantage when we use transformer in our circuit. And the design complexity is more and frequency response is also poor. These are all the advantages and disadvantages about the transformer coupled Class A power amplifier.